Okay. So today is the last one, the last lecture. So today I'm going to try to relate these expressions, not to try to obtain the Laurent polynomials, the Laurent polynomial expressions of cluster variables and other elements of cluster algebras. Doing something different, doing something more representation theoretic, and I hope 90 minutes is enough to do this, and not that I don't run out of time. So the first is to say a little bit about. Can you read, or is it too small? Yeah. Okay. About path algebras. Yeah. So remember that I have I'm working with quivers, which the two acyclic quivers correspond to skew symmetric matrices. But so take any quiver. Yeah, and such a thing, so which it's a finite directed graph, has an associated path algebra over any given field. But today I'm going to be working only over the complex numbers, and I'm going to denote the path algebra like this. So this is the path algebra. How is it defined? Well, first, as a vector space, as a complex vector space, it has the basis of all oriented paths on Q, finite paths. So the basis of all oriented or directed paths on Q is a basis. So is a basis, let's say a C basis of Q by definition, where here in that set of oriented paths, I consider for each vertex of the quiver, we introduce a path of length 0, like a formal path of length 0, which if you want to think about like the category associated to Q, would correspond to the identity morphism of the vertex seen as object of this category. Yeah? So there is a EI, let's say. This is the path of length 0, at EI. Okay, and then the multiplication of CQ is induced by a concatenation of paths. So multiplication in the path algebra is induced by path concatenation. Yeah, and by this, what I mean is that if we have two paths, let's say P and Q, we define P times Q. We let it be. We write the paths, from right to left. So somehow I think that Q, when I write it down, is a path written right to left, and Q is also a path written right to left. Okay? So this product, we define it to be the concatenation if the terminal point of Q is the starting point of P. Yeah? So it's PQ if I can say maybe that the head of Q is equal to the tail of P. Yeah? Kind of whatever. Yeah, so the terminal point of Q is equal to the starting point of P, And if they are, so in other words, if they are if they can be concatenated, right? So if they can be concatenated. And it's the product, we define it to be 0 otherwise. So if Q ends in some vertex different from where P ends, then the product is defined to be 0. And then what can we do? Well, we have this basis by definition of CQ. No, it's not Q, it's CQ here. So what can we do if we already know the product of any two elements of the basis? Is just extend bilinearly. Yeah? So that is what I mean by this. So it's the bilinear extension of this rule. Okay, so of course it's not depending on Q. For most choices of Q, this is a non-commutative ring. Right? But as an example where we do have commutativity is let's say take a quiver with just one vertex and one loop, and then let's call this I don't know A, then or let's call it X, capital X, let's say capital X, so that you see C of this Q is well, it's practically just the polynomial ring if you think about it. Yeah, but it's typically non-commutative. Like even if you put just two of these, like X and Y, this is the so-called free algebra into variables, but not commutative. So X and Y don't commute. Okay, and of course, there can, in an arbitrary quiver, there can be paths that can be concatenated one way, but not the other way. So one way is not 0, the other way would be 0. Okay.
Sorry,
yeah.
Isn't that if you don't have something like the first picture you draw, then you don't get commutativity?
Yes.
Something commutative apart from the
right. Yeah. So yeah. But I didn't want to make the claim not to think about it live, okay, on the fly. But yeah, it seems to me that this is the only way you can get something commutative. Okay. Yeah. Or let's say or just vertices but without arrows.
Yeah.
Then you get a semi-simple ring because you only have the paths of length 0.
Yeah. Okay.
Yeah.
Okay. Mm-hmm. Sorry.
Mm-hmm. But yeah, it's most of the times it's not commutative. Yeah. Okay. And here one thing is that this is not hard to see, that the category of modules over this algebra is equivalent to the category of representations. So of representations of Q. So let me just say what a representation of Q is. So a representation of Q is a pair. Let me call it I in the vertices, and A in the arrows, yeah? Such that consisting of for each vertex a vector space and for each arrow, let's say from J to I in Q. So for each arrow of Q, MA is a C-linear map from MJ to MI. Yeah, so that's a representation. So you just put vector spaces on the vertices and linear maps on the arrows, but of course the linear maps going from the kind of connecting the corresponding vector spaces that you already put on the vertices. And this is like, let's say, a lemma, which is not hard. Not hard, but I would say very important. That the category of representations, let me call it maybe capital rep CQ, yeah, of representations of Q. Maybe let me, to save some time, let me not write all of it. Is equivalent, C-linearly equivalent to the category of left modules over the path algebra. And of course, here I haven't told you what the morphisms are, but if you already have an assignment of vector spaces for the vertices and linear maps, and you have another such, then what can be a morphism? Well, a collection of linear maps from connecting the vector spaces attached to the vertices, making every diagram commute, right, for every arrow. So what else can it be? And I'm not going to give the proof of this lemma, but somehow the idea is that the linear maps attached to the arrows give you the I mean, you have each arrow is an element of the complete, not complete. Whenever I say complete path algebra, please don't listen to the word complete. Okay. So A is an arrow of the path algebra, and then giving you a linear map for the arrow. Somehow I'm telling you what the action of the arrows is, and then how can I form a module? Well, I can take given the representation, I can take the direct sum of the vector spaces attached to the arrows. And that's my underlying group for the module. And then what is the action of an element of the path algebra? Well, let's say an action of a path. Well, I define it to be just the composition of the actions of the arrows that conform the path, and then a linear combination of paths. Well, I just take the corresponding linear combination of the linear maps that I already defined. So somehow what a representation is giving me is the minimum information I need to construct that module. You see, and then there is a way to go back by realizing that the one of this ring is a sum of certain idempotents, and those idempotents being the paths of length 0. So here one can, let's say, the one of this ring is this sum, and these EIs satisfy certain properties, like they are idempotent, and they are mutually orthogonal. And using these two properties, you can take any module and then express it as a direct sum of vector spaces for the vertices. Yeah, and then after that, then you have a whole action. Okay, you just keep the minimum action, the minimum information. So that's how you go from here to here. Yeah? So this lemma is easy. So that one can just focus on this, because somehow the way to think about this lemma is that in this category is like very visual. Right? I mean, one can just see the modules here. Okay, as graphical things, rather than more abstract things. Okay, now the next. potentials and cyclic derivatives. Potentials and cyclic derivatives. Just one more comment, sorry, about the previous one. So, for example, if you think about the example of the polynomial ring, what the lemma, the way to interpret this lemma is by saying that to give a module over the polynomial ring is equivalent to giving a vector space with a linear endomorphism, right? Which is that is like in the basic algebra textbooks. Right? So it's a generalization of this is a generalization of that fact. Okay, now potentials and cyclic derivatives. Let's define the notion of potential to be a potential on the quiver Q to be just a linear combination of cyclic paths. See, linear combination of let me just call them cycles of length, of positive length, length. When I say positive length, I'm just excluding the paths of length 0. So I don't in the definition of potential, paths of length 0 are not present in that linear combination. Only paths of positive length. Cyclic paths of positive length. And so, for example, let's say 1, 2, 3, alpha, beta, gamma, and then examples of potentials. One is like alpha, beta, gamma. This is one potential. Let's say S, and then W. Another potential would be, for example, alpha, beta, gamma, alpha, beta, gamma, and they are two different potentials, right? I could take a third one, which would be like S plus W, and this is another yet another potential, right? So, and also if you think about this, all my potentials are these ones, not all my potentials, but the potentials I've written down, they all begin at ending at 2. But of course, that's not a requirement. Yeah? So like beta gamma alpha is another potential, and then beta gamma alpha plus this W is another potential. I mean, in other words, the cyclic paths, there is no constraint in where they start and end. Okay, and the point of a potential is that it has cyclic derivatives. So let's say for a cycle, let's say A1 blah 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 AD on Q, and an arrow, let's say alpha in an arrow. So Q1, by Q1 I denote the set of arrows. So set of arrows. So Q0 is the set of vertices, Q1 is the set of arrows. The cyclic derivative. Of the cycle with respect to alpha, and I write kind of partial with respect to alpha, A1 blah 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 AD, and I do the same that we do, that the usual formal derivative, or like the derivative from calculus, but kind of just the formal behavior does, which is I look, but now here I look at each occurrence of alpha in the path, And for each occurrence, I take I delete it and take the rest and think of, and form the corresponding path. So this is from L equals 0 to D. Sorry, L equal 1 to D of Kronecker delta alpha AL, just to look for the occurrence of alpha, and then say A L plus 1 dot 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 AD A1 dot 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 AL. For example, let me take this too. Sorry? L minus 1. Yes, you're right. Yes, thank you. So example, let me take the ones above, and then, for instance, a cyclic derivative with respect to alpha of S is beta gamma. This is an S, not a delta. S. It's just beta gamma. Thank you. And cyclic derivative, let's say, with respect to beta of W is there are two occurrences of beta, and for each occurrence there is a contribution. And then for the first occurrence is gamma, alpha, beta, gamma, alpha. So for the first occurrence, this alpha here is this alpha. And then plus the same thing. The second occurrence is gamma, alpha, beta, gamma, alpha, where this gamma is this gamma. So, and then here, okay, coincidence that it's 2 times, right? But it could be for an arbitrary quiver, it could be that an arrow occurs several times in a path, in a cycle, but the contributions are really different. That is perfectly possible. So the fact that these contributions were the same is actually kind of just a coincidence, just because W has certain rotational symmetry. Okay, and then what is the cyclic derivative of an arbitrary potential? It's for each cycle I know what to do. So just the linear extension of this. So the C linear extension of this rule, and we have a cyclic derivative with respect to any potential, with respect to alpha of any potential. And this is always an element of the path algebra. Okay. Now, okay, so going back, the point of having the point of a potential is that it has cyclic derivatives with respect to each of the arrows. So we have there is, for a given potential, a given potential gives rise to as many elements here as arrows the quiver has. And what's the point of that? The point of that is that now I'm going to quotient the path algebra by the two-sided ideal generated by those elements. Yeah. So in the end, really having a potential is a nice way to encode that what I define in the end is a certain quotient of the path algebra, and this path algebra is the so-called Jacobian algebra. So the Jacobian algebra. of a quiver with potential. Let me just abbreviate saying QP for quiver with potential. QS is I'm going to call it calligraphic P of QS. Don't ask me why I use the letter P. I don't know. I'm just following Derksen, Wiman, and Celebinsky. I should ask. And this is the two-sided ideal generated by the cyclic derivatives. Considering with respect to all possible arrows. And by the way, this two-sided ideal, we call it the Jacobian ideal. Okay.
And just to make sure,
Yes.
take alpha not in the cycle with 0.
Yes. Yeah. Because all the are 0, or if you want kind of this, yeah. When it doesn't make sense, you just set it to be 0. Okay, so as an example, two examples. Let me write two examples. One is, one is this one again. Let me do just with respect to the first one, because actually the second one, it's more problem. I'm not going to say what it is, but for example, here, the Jacobi, I know that the module category of the path algebra is equivalent to the category of representations. So the category of modules over this one being a quotient of this ring, this category is equivalent to a full subcategory of the category of representations of this one, right? And the cyclic and it has to be those representations killed by the cyclic derivatives. But the cyclic derivatives are partial of S is beta gamma, and then partial beta is gamma alpha, partial gamma is alpha beta. Yeah. So PQS mod is equivalent to the category of representations of reps annihilated by beta gamma gamma alpha alpha beta, which means the representations, let's say M2, M1, M3, and linear maps M gamma, M beta, M alpha, well, such that these compositions are 0. Okay? This composition is 0, this composition is 0, this composition is 0. Yeah? So that's kind of the nice thing about this lemma, this basic lemma, that I'm certainly visualizing this category of modules as just this. So for example, writing C, even C here, but then say 0 map identity, that this is a representation. This is one of these representations, so it really represents a module over that Jacobian algebra. Okay, that's one example. Another example, let me write, this is another typical example. I don't know, 1, 2, no. It's 1, 2, 3, 4, and let's say alpha, beta, gamma, delta, eta. Yeah, and then take S equal to alpha, beta, gamma plus alpha, delta, eta. Then cyclic derivatives, you see all the cyclic derivative with respect to alpha is of course beta gamma plus delta eta, because alpha appears in those two paths, and we said that it's linear extension. The cyclic derivative with respect to alpha is the linear extension of the other construction. Yeah, and then we have gamma alpha, and gamma alpha and beta alpha. Sorry, and alpha beta. Those are the cyclic derivatives with respect to beta and with respect to gamma, respectively, and same thing on the other side. So I have a cyclic derivative with respect to delta is eta alpha, and with respect to eta is alpha delta. So those are all the cyclic derivatives. That's the Jacobian ideal in the path algebra. Yeah, and then here, what are the representations that correspond to the modules over the complete path algebra? Well, this would be the representations M4, M2, M1, M3, together with with the linear maps. These ones eta, gamma, alpha, beta, delta, with which properties, what do the linear maps have to satisfy? Well, all these compositions have to be 0, and here we have some sort of anti-commutativity, right? I mean, this composition has to be equal to minus this composition. So, okay, so you say, okay, I don't like anti-commutativity. Okay, then let's change the potential. Yeah, and then here, of course, I can put minuses here somewhere, you know, in these ones. But when I take the Jacobian ideal, putting minus or not is the same. Yeah, and by the way, the Jacobian algebra with plus is isomorphic to the Jacobian algebra with minus, for example. And this you can see by sending, you know, let's say by sending delta to minus delta. Okay. Right. So those are representations.
Sorry.
Yes.
Are the generators of the Jacobian ideal minimal?
In
You can get maybe the first one.
no, for this example, they are minimal. They are for sure minimal. Yes, and in general, sorry. In general, I'm not sure. In general, I don't know.
I don't think so. I think that there are some examples where
Yeah, where it's not minimal.
Not where it is the minimal, but also
Where it's not the minimal.
I need to think about it, but I think so.
Yeah, it may be. Yeah. Yeah. Okay. Yes. Sorry. So maybe later we can discuss. Okay. So the whole point is what is that in the end potentials encode through the consideration of cyclic derivatives certain type of ideals which we call Jacobian, and in the end we fixing a potential means focusing our attention into the representations annihilated by the cyclic derivatives. So that's the whole point of taking, not the whole point, but one of the points of taking potentials. Okay, now suppose that I have a QP. So this is going to be the injective G vector of a representation. Yeah. So suppose that QS is a QP, a quiver with potential, and suppose M is a representation of, you know, how do I call it? I mean, let's say if the category of representations is rep CQ, so I'm just going to say rep, it's capital rep, no, small rep, C, QS, right, for the category of representations annihilated by the Jacobian ideal. I'm not going to write it to save some time. And rep, small rep, just to say that M is finite dimensional. Right? So M finite dimensional over C. Right? In other words, all the vector spaces attached to the vertices, which are finitely many only, are finite dimensional. Here, I also need to assume that the Jacobian algebra is finite dimensional. But yeah, so I'm also assuming that one can lift that assumption, but it's not entirely trivial to lift it. So I'm assuming that the Jacobian algebra is also finite dimensional. Yeah. It's an assumption that can be lifted. Okay, and now consider a minimal injective presentation of M in rep QS. So what does it mean minimal? Well, it means that to begin with, here, what I'm going to write here is an injective envelope of M. So this means that this one is injective envelope of M. And second, you know, for the minimality, right? And second is that when I take the co-kernel, then the next one, this one, becomes a minimal, an injective envelope of the co-kernel, right? Where of course it's not really this map, but the induced map. Right? So this is injective envelope of co-kernel of let's say, I don't know how to write it. Let's say J and no, J is a vertex. So epsilon maybe, epsilon 0 and epsilon 1. Yeah, so of co-kernel of epsilon 0. Yeah, the induced one. Yeah. And of course that this is a part of an injective resolution, right? So the beginning, the beginning or initial segment of injective resolution of M. Okay, so I consider that, and now we consider the decomposition of these two as direct sums of indecomposable injectives. Yeah, and here I'm going to use the fact that which requires certain discussion, that for each vertex of the quiver there is one indecomposable injective module or representation of the Jacobian algebra. And and that that these in the composable injectives that the vertices of Q give rise to are all possible in the composable injectives. So that.
Can you describe what an injective envelope is?
Yeah, I'm tempted to say yes. No, sorry. Like let me give an example. One example, and this is more or less how it actually works in general. For example, take for this one, with this zero relation, so the Jacobian algebra that we saw first. Take for example this one, which is a simple. That is a simple representation, or if you want the corresponding module is simple because it certainly doesn't have non-trivial submodules. Right? Okay, and then its envelope, and then first of all, here, how do the injectives look like? So one rule that one deduces is that somehow the corresponding injective is given, and what I'm about to say is not entirely true, but is given by the paths of Q that end in the vertex and are not and don't pass through relations. So in other words, the injective of this one, the injective corresponding to this vertex of the quiver, is this one with the identity here. So this would be the injective at this vertex. Yeah, so what we are seeing here is the simple representation at that vertex and the injective representation at that vertex. And and this is an injective envelope. No. And the injective envelope is, you see, what's the morphism? We said that a morphism of representation is linear map from here to here, linear map from here to here, linear map from here to here, making all possible squares commute. Right? So how do I send it? Well, I just send this one through the identity, and then of course here I don't have option. 0 has to go to 0, but notice 0 followed by the identity is 0, and 0 followed by the identity is 0, so it commutes, and same thing here, right? 0, 0, and that's the injective envelope. So somehow what one does, it's more generally, is given a representation, one looks at the suckle. Yeah, let's say in the composable, one looks at the suckle, which is a certain sub-representation, and then for each direct summand of the suckle, one plays this game of somehow from this space, throwing back, taking the paths ending at that vertex, but that survive the relations, and that's kind of in a nutshell the way it's computed. And here I'm using the fact that in general, when for any ring, the injective envelope of a module coincides with the injective envelope of its suckle. So it's enough to consider the suckle, and for the suckle, you decompose into direct summands, and it's enough to take each simple, because suckle is functorial. I mean, because suckle opens direct sums. So yeah. Okay, so that's more or less. And then the thing is, here this one can be decomposed as follows. So let me do some copy paste. And when we decompose, it's something of this form. I in Q0 for each vertex, I have the injective there, I, and then with certain multiplicity, let's say AI, and then I in Q0, and again with certain other multiplicity. And okay, and then we define the G vector of M, the G vector Gm is by definition the vector formed by all possible differences. Well, not all possible difference, sorry, by you know, like this one minus this one entry by entry. So in other words, the G vector somehow keeps somehow track of how a minimal injective presentation of M looks like. Some people call it co-presentation instead of presentation. Okay. I say somehow because at least a priori it may be that there are some cancellations in some entries, and then when recording this vector, you a priori you may be losing information of you know, if for some i's for which both AI and BI are positive, for example. Okay. In the end, for the nice representations, one doesn't lose that information. But I'm not going to go more into that. Okay, now 42 minutes. Okay. So now, why all this? Because the thing is that every triangulation, well, we know that every triangulation has an associated quiver, but if you look a bit, if you stare at it, if you stare at the picture of a triangulation a bit longer, then you realize that you also have like an obvious potential. So suppose we have a triangulation. It's a triangulation of, and here it's any surface with marked points, oriented surface with marked points. The surface can have non-empty boundary, that's allowed, but not necessary. Okay, now I'm just going to define it in a picture of an example. In two pictures. So in one of them, I'm going to take the unpunctured hexagon, and in the other one, I'm going to take the once punctured hexagon. Later, if I have more time, if I have enough time at the end, which I don't think so, I can give some like some example in a torus or something like that, but the principle is really the same. Here, well, because of the Teichmüller space, we do draw these arrows, and here, I mean the arrows. What I mean these arrows, what I mean is that the arrows whose vertices are the boundary segments. and also here is one point where I really do want to include these ones. Sorry, these arrows connecting these ones, I think. Yeah, so I have the quivers. Oops. Okay, and then looking for an obvious potential means look for obvious cycles, for the most obvious ones, and take them, right? So here, I mean, I would say this one plus this one plus this one plus this one. Obvious, no? And here I can say, okay, yeah, you have all the same obvious ones. Yeah, but you have another obvious one because you have this in the puncture. You see the configuration you have is this. So at the puncture, you actually have also an obvious cycle and somehow going counterclockwise around the puncture. So we take, let's say, this one. So let me call S of t. Let it be the sum over all triangles of alpha triangle, beta triangle, gamma triangle, where of course here I tried not to repeat the triangle, right? I mean, it's so here for each triangle I have to make a choice of either alpha beta gamma or beta gamma alpha or gamma alpha beta, just to avoid repetitions, just to avoid a term appearing 2 times. That's it. Okay, and then, minus, see if you don't like anti-commutativities. So just in order to have commutativity relations, over all the punctures, let's say this puncture, and let me call, let's say A sub A P1, alpha P1, alpha P2, etc., alpha P V sub T of P, where of course here I'm denoting, this denotes the valency of the puncture, and what I mean by this is that I take the cycle only once, but of course formally, I could consider the square, which is formally really a different cycle. I don't consider that. I consider the simple cycle in this sum, and I do that for each puncture. Yeah. So this is quite obvious to take, right? And maybe here what I'm going to say is that Derksen, Wiman, and Celevinski developed certain mutation theory of quivers with potential. So I'm not going to write this just to save time, but we know how to mutate quivers. And now that we also have Jacobian algebras given by quivers with potential, we would like to be able to mutate not only the quiver combinatorially, but we would like to mutate the quiver with potential, and actually we would like to why? Because if I take another triangulation, let's say this one, I have another quiver with a different quiver with a different potential. And what would be nice is to try to relate the module category of the Jacobian algebra of this quiver with potential with the other one. So kind of the best or the nicest would be that there would be some functor between the module categories, or that the module categories were equivalent, but this does not happen. But there are some other relations, and the way to other relations, I mean, between the module categories of these two. And for this is that Derksen, Wiman, and Celevinski developed a mutation theory of quivers with potential in order to perform mutation of quivers not only combinatorially but algebraically, and also at the level of the module categories. I'm not going to say more about this. And then something that I proved in a part of it in my thesis and another part when I was a postdoc is that so this I did in the end in 2012 is that if two triangulations are related by a flip, let's say T and T prime related by the flip of certain arc that I'm going to call K. So the arc is the name of the arc is K. Then when one takes the mutation of the quiver with potential that one reads with T, this is not entirely equal, but is isomorphic in a very well-defined way to the quiver with potential that one reads directly from the other triangulation. So in other words, the obvious way of reading a potential is nicely behaved with respect to this other mutation theory of quivers with potential that I really don't have time to present. I mean, we have a reading seminar, and it took us 10 sessions of that seminar to be able to describe all this theory of how to mutate quivers with potential. So I'm not going to do it in 5 minutes. Okay, where this is of Derksen, Neumann, and Celebinsky. Which is also a bit unfortunate because even though it took us 10 sessions, all the basic ideas of how this mutation functions, how it works, all the ideas are very basic, very elementary. Okay, anyway, so that's the quiver. It's possible to define a quiver with potential for a triangulation. Yeah, so for a given triangulation, then we can start considering the representations of the quiver with potential. Right? So, okay. So I still have 2 more sections, and I have 32 minutes. So 5 is laminates and laminations. Yeah, but of course, I'm going to try to exploit the fact that the quiver with potential is drawn on the surface. I mean, like here, for example, on the left, I can say, you know, in the end, the Jacobian algebra is you know, you have the arrows and you have all these compositions must be 0 in any representation or any module over that path algebra. Similarly here, except that now, you know, sometimes when an arrow appears in two terms, you have a commutativity. So this has to be equal to this in a representation. Yeah, for example. Yeah. So when there are punctures, the relations are a bit more complicated. That's what I'm saying. But I can still say, okay, but I can still do things very visually. Yeah, etc. Some of these are wrong. Sorry, this is wrong. 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 The other way around. Sorry. Okay, I shouldn't have begun doing this on the fly. Sorry. So let me just erase it, just to. Yeah. Yeah. Anyway. So what is a laminate on the surface? So a laminate on my surface with marked points is a curve, and I would prefer to say a one submanifold, a one-dimensional submanifold, but let's say a curve which doesn't have self-crossings. Without self-crossings. So really an embedded one manifold with certain properties. And I will probably not list all of them. One of them is that now it never passes through marked points. It's a curve. Let me call it gamma, such that gamma does not pass through marked points. Yeah, but 2 may be closed, and if it's not closed, it goes from a boundary segment to a boundary segment. So it's either closed, or with endpoints in the boundary. Sorry, that's not completely correct. Either this or, sorry, let me correct that. There is a or, and one of the following happens. An endpoint, so or, given for an endpoint, I have either that the endpoint is in a boundary segment. So here what you are seeing is the boundary. This is the boundary. So the surface is like on this side. This is the surface, and then my curve gamma ends in a boundary segment. That's that is a possibility for an endpoint. Yeah, or another possibility for an endpoint is that, bless you, is that I have a puncture, and the gamma is not compact, but it spirals towards the puncture. Yeah? So. And how can it spiral? Well, either clockwise or counterclockwise. Bless you. Yeah. Or gamma goes like this. In it doesn't touch it. It doesn't touch it. Or the other. Etc. Or if this is not closed, right? If gamma is not closed. Okay. This is for the endpoints. Yeah. And 3, gamma is not contractible. And also not contractible to the boundary, and not kind of not. And let me just make a picture. So, for instance, if I have my surface and the boundary is here, this is not allowed for gamma. Not allowed. But there is one more configuration not allowed, it is less intuitively. It is intuitively harder to justify why one excludes it. So I'm not going to try to justify intuitively why one excludes it. I'm just going to tell you that this is excluded. So in other words, when the curve goes from a boundary segment to a consecutive boundary segment.
So here, the marked curve, so that if it has boundary segments, then each segment contains at least one marked point. Something like this.
No. Sorry, here? Here you mean here?
I mean in general, the marked curve. Sorry, the marked surface that you take. If it has boundary segments, then is there a condition like last time? I remember that every boundary segment needs at least one marked point.
Yes. So that's in the condition here. Yeah. I'm assuming that. Yes. Yeah. Here. Yeah. So I'm assuming that M is not empty. It's finite. Yeah, and at least at least 1 point from each boundary from each connected component of the boundary of sigma. Yes. Yeah. So let's say here examples. Let me say I have 24 minutes. So example here, and here of course I didn't even draw the 6 marked points on the boundary, right? I mean here, but okay. But, yeah, and then the notion of lamination doesn't even refer to a triangulation, right? I mean, it's independent of, it's a completely independent notion. So, for example, here, this would not be a sorry, I'm still speaking about laminates. This would not be a laminate. This is not a laminate, but this is a laminate. So this would be a laminate. Another example of a laminate, like for example this one, etc. Right? One more thing that I'm going to exclude, it's in the case of punctures. In the case of punctures, I'm going to exclude also the simple loop around a given puncture. This is you know, when with the curve like that there are no where this is really contractible to the puncture. That's the idea of what has to be excluded. This is excluded. Okay. Yeah. So in the case of the hexagon with one puncture, another example would be for instance. Yeah. Let me erase. I mean. Let me erase these two. Yeah, and I have this. So for instance, this curve. Sorry. Yeah. So and let's say this curve would be a laminate. If there are two punctures, for example, let's say this and this, then this would be an example. So spiraling around that puncture, and at some point going to the other one and also spiral. Yeah. Okay. And then here I maybe I made the well here I here the spiral sense is clockwise in both, but it doesn't have to be. It could be like clockwise, but then counterclockwise. Those are examples. Okay. Now there are two things. One is that with respect to a triangulation, sorry. Before I have to say what a lamination is. So definition. A lamination of the surface is a collection of laminates. Is a finite set of laminates. That do not intersect each other. That do not intersect each other. Yeah. Yeah, another thing I have not said is that actually we consider laminates up to isotopy in sigma minus m. Yeah, to isotopy in sigma minus m. And so and also with laminations. So if you think about giving a lamination, somehow it's equivalent to giving a set of different non-crossing laminates, pairwise non-crossing, together with a multiplicity for each. Because for instance, this is a lamination where you only take one, but then this is another lamination when you take kind of two copies up to isotopy of the same spiraling curve. So you can say it's equivalent to giving this one with multiplicity 2. And they are two different laminations. Okay. Now, what's the point? That there are the shear coordinates. Yeah, so which are the shear coordinates of a lamination with respect to a triangulation. Yeah. So T is a triangulation. Yeah. And then the shear coordinates, it's going to be a vector indexed by the arcs in T. Yeah? So we have the triangulation T. We have a lamination L, let's say. This is like MATBBL. And the vector of shear coordinates is T of L. And this one is a certain thing indexed by the arcs, which I'm going to still call I, yeah, in T. And I just have to tell you for each I what's the corresponding entry. And for that I'm going to assume that T is nice, so that it's not a very degenerate triangulation. And then for each, in such a case, given an arc in the triangulation, it sits as a diagonal in a quadrilateral of the triangulation. So let's say that this is I, yeah, sitting as a diagonal in the quadrilateral, and then I'm going to count the following two things. So copy, paste, and I'm going to count how many times the lamination I crosses I in such a way that the configuration, the way it crosses the whole quadrilateral is like this. I'm going to count how many times, and I'm also going to count how many times it crosses it like this. So what's the difference? That in this configuration, the crossing draws an S shape on the quadrilateral, whereas in the second one, the shape the crossing draws on the quadrilateral is that of a Z, a letter Z. Right? I mean here, like if you enter and you start, if you start, yeah, it's S, and here when you enter, it's a Z. So we count and we take the one number minus the other. So of course, it may be that it doesn't cross at all in either way, in which case it's 0. But for instance, if it crosses at least once this way, it doesn't cross in this way and never ever, because it doesn't cross itself, because the lamination doesn't have crossings. So if it crosses this way, it doesn't cross this way, and the other way around. If it crosses this way, then it cannot cross this way because it's a lamination. It doesn't have crossings. So in other words, when I say this, it's really either always like this or always like this, and it's just this with positive sign, this with negative sign. And that's what and this counting is what we put here. Yeah. So maybe just to emphasize that we have to count all of them. Maybe let me write here number and number. Yeah. And then, for instance, the crossings of this, like that happen just in corners, I completely ignore them. And the fact that we completely ignore those crossings, those possible crossings along corners, implies that this that each of these is always a finite number. So this the vector of shear coordinates is actually a how do I write here? It's actually an integer vector, z to the t. And actually, a result of Thurston that I think he either never published the proof or thought that it was obvious, which is that for a given triangulation, the assignment L to shear coordinates is a bijection between the set of all laminations and z to the t. Okay. 13 minutes.
So
Okay.
just ask
Yes.
a question. So you said that it's impossible that the crossing is, let's say, from the top to the right, or top to the left, or that we ignore it?
No, you ignore it.
Okay.
Yeah, it can perfectly happen,
Okay.
but that doesn't enter the count. Yeah.
So in general, it says ignore crossings involving laminates that connect to adjacent boundary components.
No, this is slightly different because these are not boundary components. So for example, it could be that, for instance, you can even be in this situation, and for instance, your eye looks like this. There could be some other punctures. Let me draw it again. There could be some puncture here, some puncture here, some puncture here, some puncture here, and the arc eye could be this diagonal, and you may be looking at this. In which case, this would not be contributing because the crossing is happening along a corner of the quadrilateral. So it's kind of you really like when you look at this, somehow in a way you are not you are kind of forgetting all the outside, right? But the fact that I am ignoring the corners means that if the triangulation was like this, there are infinitely many crossings here, but none of them counts. And infinitely many crossings like this don't happen. Don't happen. Why? Because if it happens, it's because it has to spiral towards some puncture. But once it starts spiraling, it stops doing these crossings. So. Okay. So 10 minutes. So I will at least, so I will at least say about the G vector. Yeah, so now the point is that each laminate, and this is more, at least when there are no punctures, this is very clear. So now from now on, for simplicity, let's just suppose that sigma has no that the surface has no puncture, so that all marked points are in the boundary. But it's just for simplicity of the final result still holds when there are punctures. Yeah. So the thing is, each lamination gives rise to a representation of the quiver with potential for any triangulation. So you see, now you fix a triangulation, and each lamination gives a representation. So this is like L. So I'm just going to illustrate how it goes. Yeah, just let's say here, and I'm going to illustrate only for laminates, because what one does is for each given a lamination, one considers the connected components. Each connected component is a laminate, and then one defines the representation for each laminate, and then for the lamination is just the direct sum of all the others. So I'm just going to consider only this. So let me draw the triangulation. Yeah. Okay. And now what I'm going to do in this case, since it's a, what I'm going to do more systematically, what I do to define the representation is I'm going to consider. Let me see. I'm going to consider each endpoint lying on a boundary segment, and I'm going to move that endpoint towards the next puncture. Going in such a way that what does it mean next? That in traversing this boundary segment, the surface is on the left. And I do this for each endpoint of the laminate lying on a boundary segment. So, oops. Yeah. Yeah, and of course, what I obtain is not a lamination, right? Because now it ends in marked points, which we said, okay, if it ends in a marked point, we don't call it a lamination, right? But so here the curve would be this one. Okay, and now for this one, what I do is this was not a good choice. Let me choose another one that makes it easier. I mean, it was not a good choice of laminate for the linear maps of the representation. So let's say if in the end I want. Let's say that in the end, I'm going to just reverse engineer what I want. So if I have that, I have to move to the right. So it's this. Yeah. So this would be my lamination, and then, as I said, on each boundary component. On each boundary segment on which the laminate has an endpoint, move the endpoint towards the next marked point, traversing with the surface on the left, and then so you obtain this. I would say that that's clear. And this way of sliding endpoints, this is what you always do. okay, to obtain this. And then for this, I would say that there is an obvious representation, because if you draw the quiver on top, etc. You know, in this case, we know that the relations are just very simple, because we are assuming that there are no punctures. And in this case, it's obvious that there's a nice representation associated to it, right? I mean, just put complex numbers for this crossing, complex numbers for this crossing, an identity for the fact that this segment connects these two consecutive crossings. Okay. I'm not going to be able to illustrate nicely. That's the way I wanted. But let's say that this representation is MTL. Is the representation that I just described. That I didn't write down. And the thing is this, for instance, this is something I proved in my thesis, is that yeah, I mean, in hindsight, it's not that hard to prove, but it's that the G vector of this representation is equal to the vector of shear coordinates of the lamination. And here with certain kind of small, very small technical caveat that I just don't have enough time to explain now. It's very small. It's something almost insignificant. Not almost. It's something insignificant. Okay. Okay. And now I'm going to try to do something more, because this is still, it's like, so what, right? I mean, where are the cluster algebras, right? I mean, there has been no cluster variables at all now. So let me consider the F polynomial of the representation. Yeah. Let's say MTL, although this is something you can define in general, which is the generating function of subrepresentations of M. So this is for each dimension vector. So this is Z to the Q0, and then non-negative, because they are dimension vectors. Of, you know, and then you record it in a generating function, so it's x to the e. Yeah, and then you want to count subrepresentations, so it's kind of a, you know, like for the vertex with exactly one point, you put an n-dimensional vector space, and then the generating function, I mean, it's going to be the, you know, all possible Grassmannians. Okay, but they are not finite, so you have to put Euler characteristic. Yeah, of the now it would be the quiver Grassmannian of all subrepresentations of M. And then define the CC map. C for Calderon-Chapoton. Of M, and this is of course with respect to the Jacobian algebra. Because if you notice, the G vector depends on the Jacobian algebra, because it depends on taking a minimal injective presentation with respect to the Jacobian algebra. So it's injectives for the Jacobian algebra. Okay, this of M. Would you give me 5 more minutes? Yes, I mean, I'm almost. Yeah, let's say TL, and then define this as G, sorry, not G, it's, let's say, U, and here I'm already thinking that U is certain cluster of a cluster. That I'm thinking already that U is the cluster sitting inside a seed that has Q as the corresponding combinatorial datum. Okay, this U to the G vector. And then times and evaluating that F polynomial. Sorry, this is called F polynomial. F, if I'm not mistaken, F is for Fibonacci. Although the ones who defined it were Derksen, Wiman, and Televinsky. And this F of M, TL, evaluated, it's not entirely that polynomial, but you have to evaluate it in U, and then take B0, let's say underline, B1, sorry, B1 underline, and I'm going to explain what that is, etc. UN underline. Yeah, and sorry for time reasons, I'm not. There are certain also small technical caveats that I'm not skipping, but okay. But here this B underline J is the J column of the matrix corresponding to the quiver Q. So if you remember, for cluster algebras, we started with certain matrix whose top was symmetric, because now I'm speaking of a quiver, the quiver of the triangulation. So I take the quiver of the triangulation, I consider the corresponding skew-symmetric matrix. Yeah, I put something on the bottom to reflect the fact that I'm considering these ones. You remember, as we did that time, okay? And then these ones are the columns of that matrix. So this one is like a, like a U1 to the B1J times U2 to the B2J, etc. Right? UN times to the B, what? The BNJ. Yes, and yeah, here there is a small technical caveat that I would really have to think a little bit more. Yes, okay, I'm going to say it, not to skip it. Times the corresponding Y1 to the Bn plus 1J, etc. So also the Y's included. Yn, well, not n, right? M, Bn plus Mj. Yeah, where these Y's correspond to the boundary segments, let's say. Yeah. Okay, so that now at least in here there is no more caveat. Okay, now the theorem, and this is something that actually we proved with the guys, myself and Schroer in 2020 for unpunctured surfaces. And guys, myself and John Wilson for the punctured case, but we need that the boundary is not empty, so we haven't proved it for closed surfaces, and this was in 2023. and is the following. The following set, B equal to CC of, I'm not writing the subscript for the Jacobian algebra, just directly this, such that L is a lamination of the surface of sigma m, and here T is fixed, the triangulation T is fixed. This set, which if you think about it, is a Lagrange polynomial, because this is a Lagrange polynomial and this is a Lagrange monomial. So this is obviously a Lagrange polynomial. Okay, this thing is a basis for the cluster algebra. Let's say for the cluster algebra structure of this coordinate ring of Teichmüller space, of decorated Teichmüller space. So for the cluster algebra structure of the lambda length, well, not even structure, just directly for that ring, for the lambda ring, for the lambda length coordinate ring. Of the Teichmüller of the decorated Teichmüller space, and second, always actually, for every lamination, this CC of M T L is equal to the expression given by Musiker, Schiffler, Williams, the one we saw the other day, for the bipartite graph associated to, let's say for every laminate, just to be less confusing, for every laminate L. So in other words, for each laminate, you can construct a bipartite graph following the procedure that we described last time, of looking at the crossings and somehow unfolding those crossings, and then with that bipartite graph you can count perfect matchings with weights to form certain rational functions, to form certain generating function of perfect matchings, and then divide by the crossing monomial, and then you obtain this expression. And on the other hand, you can form a representation, consider its minimal injective presentation and its generating function of sub-representations, and form this expression, and these two things are the same. And this is how all this connects to cluster algebras. And then just to close, so this is something that we started trying to prove with Christoph and Jan in 2012. So it took us 11 years to finally prove this, and we didn't even prove it in the most general case, right? Because we still don't know what happens when it's the closed surface, which in a way is the most natural one, right? I mean, the most natural type of, let's say, Riemann surface is the one that has empty boundary. Okay, so thank you.